We're going to continue our discussion of the quantum mechanics of molecules by talking about other molecular energy levels in addition to translation. And in particular, in this video, we're going to discuss rotation, vibration, and I'll spend a very brief amount of time talking about electronic energy levels that one finds in molecules. So let's start with rotation. All right, rotation, as we've seen, is just a molecule rotating in three-dimensional space. And it turns out that for linear molecules, it's actually quite straightforward to find the energy levels that are due to the waves that the particles form when they rotate in space. These linear energy levels for rotation are going to be given by again, Planck's constant squared over 2I, where I is the moment of inertia of the linear molecule, and it's going to be multiplied by J times J plus 1. And this J is an angular momentum quantum number. So it is the thing that will vary from one state to another. And it can take on values of 0, 1, 2, and so forth. Now, what about some of these other things in the formula? Well, this I mentioned is the moment of inertia of the molecule. And what is a moment of inertia? Well, it's basically a distribution of mass in the molecule. So in the case of a diatomic, it has a very simple formula. It's just the product of the two masses divided by their sum times their distance of the masses from the center of mass of the molecule. So it's going to have units of, say, kilogram meters squared. All right, and it'll turn out that all of this will work out to give the right units. Now, we also sometimes see the rotational energy written in a slightly different form, and I'll write it in red here to emphasize it, that it can be written as a constant. I'm going to put a tilde over the constant, times J plus 1. So this is a little bit simpler way of writing it. And this B tilde is something called a rotational constant. And you can see, based on its comparison to the previous formula, that it's inversely related to the moment of inertia and also to Planck's constant. Now, B is sometimes given in units of inverse centimeters. What is an inverse centimeter? Well, you can think of it as being indicative somehow of the wavelength of the wave that this rotational state represents. And if we wanted to see it as a function of joules, we would multiply it by Planck's constant and by c, which is the speed of light. So remember, speed of light is going to be in something like meters per second or centimeters per second. So if we have h in joule seconds and speed of light in, I'll say, centimeters per second, and b is in units of 1 over centimeters, you can see that the centimeters will cancel, the joules will seconds will cancel, and we'll have something that's in units of joules. All right, so the reason we use this strange unit is that this comes from the spectroscopy of these molecules. When we measure the transitions between energy levels using laser light or other kinds of light, oftentimes it's become the habit of chemists and others to use this unit to describe the positions where those absorptions might appear in the spectrum. And so it's a little bit of a shorthand, but chemists have gotten so used to it that we use it now pretty universally for a lot of different molecule level energy things. And we also use it for vibrations as well, so we'll see that in just a moment. Okay, now these rotational energy levels, you can see that actually as J increases, these are going to get farther apart. But the other thing that is true of these rotational levels is that each one of these levels, each one contains 2J plus 1 different states. So in other words, it has a built-in degeneracy. Degeneracy in quantum mechanics means that things that have the same energy. So if I have 2J plus 1 different and distinct states that have this same energy, that means that there's a lot more of these states than appears by simply the formula for what the energy levels are. Now, this is true, this formula, these two formulas, are applicable to any linear molecule. What about nonlinear molecules? Well, it turns out I can't write down a neat formula for you for a nonlinear molecule rotation. These can be calculated very readily on a computer. They have similar distances between the energy levels. Actually, they're probably a little bit closer together because the rotational constants in that case tend to be smaller. But for nonlinear molecules, we can calculate them. We just can't write down a neat formula like we can for linear molecules. So, and a lot of what we'll do, we'll treat linear molecules because I can write down an easy formula for that. But I want to reassure you that even though I'm not doing that for the nonlinear molecules, it doesn't mean that the problem can't be solved, but it has to be solved computationally. Now, let's move on and talk about vibrations. Now, a vibration in a molecule is basically the motion of two atoms relative to one another, and we can think of those two atoms as though they were connected by a spring. All right, so we might have a spring that attaches them together, something like that. And a spring has the physics that's given by a harmonic oscillator. And it turns out this is one of the problems in quantum mechanics that can be solved exactly. And it turns out that the energy levels of a harmonic oscillator can be written like this. So I'll write E sub vib, so this is a vibrational energy level, is equal to a reduced Planck's constant. H bar is just Planck's constant divided by 2 pi. So you'll see me write H bar a few times. Don't worry about it. It's also on the order of 10 to the minus 34 joules seconds. So H bar times omega, and I'll talk about this omega in just a minute, times a quantum number, which I'm going to write as an italicized V plus 1/2. And this italicized V is the quantum number for the harmonic oscillator, and it can take on values 0, 1, 2, 3, and so forth. Just as, and I don't think I wrote it down, yes, I did write it down for the angular momentum, can have any integer numbers. So these are the quantum numbers for the harmonic oscillator, and the J's are the quantum numbers for the linear rotator. Now, what is this omega here? Well, this omega is related to the frequency of the oscillator, the vibrational frequency of the oscillator. Again, because we're used to looking at vibrations using spectroscopy, we typically report this oscillator frequency in units of inverse centimeters. So once again, we're going to be able to convert it to joules by multiplying by Planck's constant and by the speed of light. I'm never going to ask you to do that. All right, we're going to compare things that are in wave numbers from one to another, so you don't have to go through all that conversion. But I want you to know where they come from, and I want you to know that it can be converted to joules if we need to. Now, this is the set of energy levels that I would have for a single harmonic oscillator. What if I have a polyatomic molecule? I know in a polyatomic molecule, I'm going to have many vibrations. In fact, I know that my energy of vibration is going to include perhaps as many as 3n minus 6 of these vibrations. So I'll have to add up from 1 to 3n minus 6 a similar sort of expression for each of these. Now, it turns out in molecules, although the oscillators are coupled to one another, that is, they can share energy among themselves, at very low energies, we can treat them as though they were independent harmonic oscillators. So I can write this just as a sum over these independent harmonic oscillators, each of which has its own distinctive frequency, and each of it which will have its own quantum number here. All right, but it's just a sum over these harmonic oscillators. So it's actually very easy to scale up from a single harmonic oscillator, like one might have in a diatomic molecule, to a whole set of 3n minus 6 harmonic oscillators, or 3n minus 6 vibrations, as the case may be. So we can do this quite readily. Now, one of the things I want to mention is that this harmonic oscillator frequency is typically quite a bit larger than the rotational constant. In fact, when I write them both in wave numbers, I find that typically the harmonic oscillator frequency is going to range from anywhere between 50 and 4,000 wave numbers. Whereas for B, the very largest B that I can quote for you is about 60 wave numbers. And the smallest is going to be fractions, so we'll say 0.001 perhaps wave numbers. So we can see here that B is a lot smaller, maybe I should even put two of these, a lot smaller than the harmonic oscillator frequencies. So we're going to be interested in what that means for the energy levels of a molecule. Now I want to finish by talking about electronic, and I'm not going to really say a lot about electronic energy levels. The reason I'm not going to say a lot is because at room temperature most molecules are simply in their lowest electronic state. So we can think of these electronic states as ranging, say, from down here to up here. So this would be the lowest electronic state, and this would be the first excited state. And to compare that, for example, to vibrations, vibrations might be spaced something like this. Okay, or even smaller relative to the electronic energy spacing. So in other words, the vibrational energy levels are much closer together than the electronic energy levels are. All right, now we've already talked about what happens in the case of rotation. So if I were to take, for example, this distance between the two lowest vibrational levels and draw the rotational levels in here, they would get farther apart, but there would be, typically, 10 or maybe 20 of these in between the first two vibrational energy levels. So there are actually, quite a few of them in there. And remember that each of these, in a linear case, has a degeneracy of 2j plus 1. So there's even more states packed in here than just the number of levels. And of course, it would continue going up. The energy levels related to nu V equals 0 here and V equals 1 here for the vibrations. The rotational levels that are built on top of this vibrational level would continue to go up even beyond V equals 1 here. So they would be contributing to a total number of states. Now, what would I see if I looked between a pair of these rotational levels? If I want to look at translation, for example. Well, it turns out they're so packed, in fact, I would have to multiply this by something like 10 to the 16th. They're so packed that these translational levels would look like a dense mass of lines that connect all of these together. And they go all the way up as a dense mass beyond the first few rotational levels, and in fact create a huge density of states for all of these energy levels that go up. So what we can see from this is that at a particular energy, let's say I want to pick an energy that's in here somewhere. Okay, well, this energy is going to translate to something up here. It's going to translate to something over here. We're going to see that there are, in fact, lots and lots of states at any energy we might choose to pick between these. But they're all spaced in a relative way that the spacing between the electronic energy levels is much greater than the spacing between adjacent vibrational levels. These are much greater than the spacing between rotational levels, and these are tremendously more farther apart than the spacing between translational energy levels. So we can get a sense here that there's tons of translational energy levels in a given molecule. There's quite a few rotational levels, fewer vibrational levels, and in the case of electronic energy levels, probably just one that's populated in any given time. Okay, we're going to talk more about what this means for molecules and what this means for our statistical treatment of molecules in the next video.